All right, guys. Hello and welcome to the first 188 section notes review. So these sections are kind of new, and their purpose is to kind of recap the material that you guys covered over the last week and to hopefully cover some of the stuff that you guys covered in section. All right, so with that, let's get started. So this week in 188, you guys should have covered search problems, search algorithms, and heuristics. So we'll cover each of those three kind of briefly. So let's start with search problems. Okay, so a search problem is composed of a couple of different parts. So first, we have the states for the search problem. And these states are going to be kind of an abstracted representation of the world state, which is going to include the minimal possible information that you need to perform your transitions and to perform your goal test. Okay, and usually when we ask you about states, kind of some of the things that we're interested in are the representation of the state and the size of the state space, which in other words is the total number of states. Okay, in addition to states, search problems also have some actions, which are fairly straightforward. If you think about the Pac-Man example, your actions are moving north, south, east, or west. They have a successor function, which is going to take in some initial state and an action, and it's going to give you a cost and a next state. So this successor function is going to determine your transitions in your state space graph. Okay, and then after that, we also have some start state and some goal test. Okay, so moving on. Okay, so also in class, you guys should have covered a couple of algorithms that will solve search problems. And kind of the first basic one that we covered was tree search. So I've included the pseudocode for tree search below. And kind of the important thing to notice for tree search is this fringe object, which is very important. So basically the fringe is going to be some type of queuing data structure, and it's going to determine the order in which we expand nodes in our search tree. So you'll notice that this definition is kind of intentionally very ambiguous. Like what kind of queuing structure do you use? So this is because there's a couple of different search algorithms which are all going to use the same pseudocode. And the way that they're different is because they have different fringe representations. So for example, depth first search is going to use a stack, breadth first search is going to use a queue, and so on. And we'll talk more about those later. Other things to notice, we have our goal test here, which is the same goal test that we talked about with our search problem in the last part. And then we have this expand function here, which is going to be basically the same thing as the getting the successors from the search problem in the last part. Okay, so another thing that you might want to note in tree search is that there's nothing to prevent you from expanding a state multiple times, right? So we just pop a node off of the fringe, and then we expand the state, and we add all the children onto the fringe. And if a state is repeated in the fringe, then we're just going to expand it many times. And so this can be expensive, and it can be wasteful, which is why the next algorithm that we showed you is graph search. So just looking at the pseudocode, you'll kind of notice that it's very, very, very similar to tree search. In fact, it's the exact same, except with kind of these three optimizations here, right? And so all three of these lines have to do with the closed set, which is new to graph search. So the closed set is basically going to be a set of states, which just keeps track of the states that you've already visited, so you don't have to expand any state more than once. So tree search with this simple optimization is going to be called graph search, and this is kind of the pseudocode that we'll be using predominantly for the rest of the class. Okay, excellent. So I mentioned a couple of different specific algorithms that are going to use this general pseudocode. And the way they're different is because they have different representations of the fringe. So let's look at those now. All right, so these are kind of the five that you guys covered in class. We have DFS, BFS, UCS, uniform cost search, greedy, and A-star search. So depth first search and breadth first search you guys have probably covered before, so I won't spend too much time on that. Basically, depth first search is just going to use a stack, and breadth first search is just going to use a queue. Uniform cost search is one of the new ones. So uniform cost search is going to use a priority queue, where the priority is the backwards cost, which we'll call G of n in this course. So the backwards cost is going to be the cost from the starting state to the current state in your node. So if, for example, we have a search problem that's something like this, and we start at state A, and we're at state C, the backwards cost at this node, so G of the path A, B, C, is going to be 5, not 3. So that's an important distinction. Moving on to greedy. It's also going to use a priority queue, but the priority is going to be H of n, which is our heuristic value. And then we have A star, which is just kind of a combination of uniform cost search and greedy search. Okay, so back to this graph search pseudocode. Kind of want to draw attention to one more thing, and that's going to be the distinction between a node and a state. So this distinction is kind of subtle, and the terminology doesn't really help too much with making the distinction. So one thing that we can just notice from the pseudocode is that the nodes are going to go on the fringe, whereas the states are going to go in the closed set. Okay? But beyond that, there's not too much that is super obvious just by looking at the pseudocode. So let's kind of talk about what the differences between nodes and states are. Okay? So starting with the state, a state is going to be a search state, which, if you'll think back to the slide on search problems, is just the state of a search problem, right? And you can think of this as a vertex on the state space graph. So we've included a state space graph below. In fact, this was the one in the lecture. And a state is just kind of any vertex here. So A, B, S, P, G, those are all states. Okay, and they're just individual search states. Now, node is going to be a vertex in the search tree. Okay, so if you recall from lecture, the search tree is the tree that we generate as we perform our search algorithm. So here you'll have kind of the search tree that's associated with this state space graph, with this search problem, where just looking at the top, starting with node S, if you expand S, you'll get the paths S to D, S to P, and S to E, right, which are all represented here. Now, another thing that you'll notice is that in this search tree, you kind of have multiple copies of a single state, right? So for this example, you have kind of 2 copies of E. So why is that? And kind of what's the difference there? Let's just look at this leftmost E first. Here, this E is represented by the path from S to D to E, okay? Whereas the central E here is represented by the path just from S to E. Okay, so from this we can kind of make the distinction that a node is going to encode an entire path, right? So the way that these two E's are different is because they encode different paths. So nodes encode paths, states are just search states. All right, excellent. Let's move on. So the last topic that I wanted to cover is heuristics. And what a heuristic basically is an estimation from every state of the true cost to the goal from that state. And we're going to use it in our A-star search and our greedy search. Okay, so there's a couple of things that we want to consider when it comes to heuristics, especially for A-star. The first of which is admissibility. And I have the definition listed below. But what it basically says is that the heuristic value at any state must underestimate the true cost to the goal. And this is going to guarantee us optimality for A-star tree search. So why does this help us? Well, it's because if we have admissibility, a suboptimal goal is never going to be popped from the fringe before a better goal is popped from the fringe, right? So I'm not going to go into the definition here, but kind of the intuition is that the F value of the optimal goal and the F value of all ancestors of the optimal goal will be lower than the F value of any suboptimal goal. Okay? So that's kind of the intuition of why it works. The next thing that we're interested in is consistency. So again, the definition is listed below. But basically, what it says is that the difference in heuristic cost between two adjacent vertexes or adjacent states must be lower than the cost of the arc between those two states. So the heuristic drop between two states must be consistent with the cost to go between the two states. And this guarantees optimality for A-star graph search. So why do we need this stricter bound for A-star graph search? Well, it's because in graph search, every state is expanded only once. So after it's expanded, it's added to the closed set. So we need to be guaranteed that when we expand a state for the first time, we've reached that state via the optimal path, right? And consistency will guarantee that. All right, so that's it for this week's review. See you guys next time.